Welcome back, everyone, to Data Science for Everyone. Today, we're going to be looking at some mathematical tools for finance, specifically approximation. Let's get started. So we're going to be working on individual basis functions today. Now, this is from last time. This is everything that we need to kind of get started with today's exercise. And let me go on and maybe make a little bit of a title for this section here. And I want this to be that. And let's say individual basis functions. So what we're going to be basically talking about with these individual basis functions, okay, is one can reach a better regression result than we've had before, okay, by choosing, again, a better set of basis functions, okay? So we're going to exploit knowledge about the function to approximate it. Now, in our case today, we're going to define it via a matrix approach, again, using some matrix algebra. And specifically, we're going to be using NumPy, okay? That's why we have this here, and NumPy arrays. And so first, let's actually do a case of monomials up to maybe an order of 3. And then we'll do this with some little functionality, okay? So let's go on and get started with that. I'm not going to rerun these because I have them ran up above, but I'll give us a little bit of space here. So first off, let's go on and create a matrix here. MP zeros. We want this 3 plus 1 length of x. Okay, and so then let's go in here and do something like a matrix 3 of all is going to equal x to the 3. Mat of 2 is going to be in here x squared. Mat 1 is going to be in here of x, and then mat of 0 is going to just be equal to 1. So let's give a little bit of a discussion about this, okay? So the first thing that we actually did in here, okay, we created an nd array object, and this is just going to be the basis function for all of our values. I can actually insert a cell below, and you can take a look here. You can see how big it is. Again, it's basically each of these are going to be 50 long, okay, and we're going to have at least 3 plus 1 of those, okay? So 3 being the number of polynomials that we want to work with, plus 1 being 0, the 0th polynomial, which is technically 1, okay, which is what we're getting here. So the base of these is going to be from a constant. That's the constant here of 1. So this is constant. This is going to be cubic. Okay, and we are basically going from constant to cubic as we go. So let me go on and run this. And then the next thing that we're going to want to do in here, let's create up our regression. And so mp dot linear algebra, because again, we're doing this via linear algebra. And then we do lst sq, excuse me, and with our matrix dot t. Dot t here is for transpose, because we need to transpose the matrix, multiply by f of x. Our cond is equal to none, and we want to just grab 0 here. And let me talk about this just a little bit, okay? So this is basically just our singular regression step that we're going to be doing. Now, we also need to actually create up our basic estimates. Excuse me. So let's do something like reg.round 4 here, and you can see here that when we actually look at these are going to be something like 0. All right, we have 0.5628, which is okay. And these are, again, here, these are optimal regression parameters. Now, one thing here, again, you can see this -0. It's because if I get rid of this, here you can see that they're actually quite small in this instance, okay? But I'm doing this 0.4 just so that we can kind of get a basic visual on what they look like. Last thing that we're going to want to do is to go on and use that create function, our create plot, and we want x of x, we want f of x, oh no, of, I'm missing an ry here. So let me go on and put that here. And we want to actually create up our ry, our predicted. So mp dot, okay, because we're doing the dot product here of the regression and our actual matrix. And let's go on and create the plot now. So we want this to be blue. We want this to be red with dotted red. We want f of x. And we want, let's call this reg for now. And we want x, f of x. So let's take a look. All right, and we can see here that this is definitely probably not the best. Okay, so this is our regression estimates. We could probably do the better again. So if we go back to our previous video, we can see here that using a 7th degree polynomial, we actually got very, very close for our estimates. But again, here we're using just a basic linear regression approach here, and it's not exactly what we want. So maybe now let's try changing this up just a little bit. We want maybe to see like what a perfect fit would look like. Specifically, let's give it a sign value. So let's do mat of 3. So that cubic we're going to be changing to something like mp.sign of x. And let's 6 sine of x. And let's actually go on and rerun that regression. F of x, r cond none, 0. All right, and then let's go on and ry is equal to mp dot dot. Here we want our regression with our matrix. Now here we can actually double check this. Do mp dot all close to actually check and see how close f of x is to ry. This is basically checking their correct values. Okay, so whether they actually match up. And now we actually see that they are true. So it's actually getting actual values in there that they are the same. mp.mean, let's go and grab the mean squared error. F of x minus r of y squared. And we're getting in here, make sure that I got all of that in. Yep. And we're getting an extremely small number in here, basically 0, as it were. Okay, so let's go on and also grab that plot. And here you can actually see that it's now leads to a perfect fit. Okay, because again we're using up that in that actual sign of x instead of just using up some in-degree polynomials as we were previously. If you guys like this, please comment, subscribe, hit that like button, and I will see you guys next time. Bye-bye.